Okay, let's see if I can try and explain what I'm talking about with relation to electric fields, sines, and signs of current, rotation of magnetic fields, and impedance. So, first of all, a positive charge, which is not about current, because current is moving, a positive charge in free space has its field lines pointing out in all directions. Okay? And a negative charge in free space, well, that one's a bit lacking, but yeah, has its field lines pointing out in all directions. Now, we know that opposites attract. So if a positive charge is near a negative charge, their lines of tension will connect to each other. They want to come together and equal zero. Potential, this doesn't have potential unless it has potential with something, and same here. But they have potential, their lines of potential make them want to move together. Now, let me point this out. If there was two negatives, they repel. Their lines of tension do not connect, and they want to move apart. This will make some mechanical logic to you if you bear with me, okay? Now, we're all familiar with a capacitor. Well, most of us are. You have your two plates of a capacitor, and if it's charged, let's say you've got your positive charge relative to the negative charge at the other side. You got your lines of tension, sorry about this terrible camera, across between the positive and negative charge, and might I point out some fringing at the edges, okay? Brilliant. Now, I'll also point out that if we spread out those capacitive plates, and I forgot to draw in the lines at the other side, there will be some weaker linking lines. There'll still be the majority of the lines of tension across between these two plates. There will be some going the other way. Same here. And then we get to a dipole, and we have lines of tension going both ways. Now this is what we would call the E vector, those lines of tension, but the sum of that E vector, and we take 9 degrees from that sum, and we have the B vector, which is the magnetic field, right? Think about it, because if this changes with relation to that, it's like moving charges along those field lines. And then it follows the right-hand thumb rule and creates a rotating magnetic field. And if it's rotating, spiraling along the axis, well, the sum of, this rotation and this rotation and this rotation is this way. Now, let's have a look at that. If a positive charge has to move or change in one direction, it will create a rotating magnetic field. If a negative charge has to move in that same direction, it will also create a rotating magnetic field, but in the other direction. So if a positive charge and a negative charge are moving in the same direction, they appear to repel magnetically. But unlike charges, attract. Okay? Now, let's jump to, an antenna. Actually, no, I'm going to jump here first. Back to the capacitor. This is very important. So, we have positive charges here and negative charges here. But what happens if I start to move in slowly with a strong positive charge, and I've moved in this direction? Well, based on the understood physics of Faraday's laws, if a positive charge starts moving in this direction, well, let's just forget its magnetic fields at the moment, that's incidental, but it's a positive charge. It's going to repel the positive charges, and it's going to attract the negative charges. So when it starts to repel these positive charges, there'll be a movement, which, based on the right-hand thumb rule, which is the direction and then the rotation, brilliant, that rotation will be out of the page and over, okay? So the positive charges will create this particular rotation, but negative charges are attracted to positive, so they're not going to push away, they're going to have a little pull back. But they're also, so they're going to go in the opposite direction. But they're also, where are we? The the opposite sign in their electric potential. So although they're going to go the other way, they're not going to create the other rotation because they're going to go the opposite direction. But they're going to create the same rotation. So what will happen in this instance is we've got the negative charges moving this way and the positive charges moving that way. We'll end up with a summary rotation, because you can't have one little rotation and another little rotation the same. Sorry, I got the arrow bad, because this and this is a conflict, so it ends up being a net rotation, and that's known as Z pinch, okay, or zeta pinch, right? But what I'm pointing out here, so I've brought in this positive charge and caused this shift or movement of charges. But at no point has this movement of charges as they moved along changed the net potential of the electric field potential of each side of that capacitor. This has still remained just as positive, and this has still remained just as negative. I pull that charge away, these charges will relax, right? The negative ones will start to relax back that way, and the positives will start to relax that way. And then we'll have a reversed net direction of the magnetic field. So what I'm pointing out is when I introduce the positive or take it away or introduce a negative, I create what we call a current along that capacitive plate, however brief, okay? And as I move it the other way, that current changes direction. But the net charge doesn't change on either of those elements or plates. So, now, let's look at a dipole. And this is where we get into impedance. So, if this is our feed point and we have two quarter wavelength elements, well, we know that these are being operated differentially. So when this becomes maximum positive, this becomes maximum negative. And we know that it goes in degrees in a cycle, okay? We've got 0, maximum positive, and maximum negative. And same here, but always 180 degrees out of phase. So when this one's here, this one's here at the source. So at one moment in time, this one reaches maximum positive, right? And that positive charge is applied here, whilst this one has reached maximum negative and negatives applied here. So now let's track over time this positive. by the time the source has gotten, this is a quarter wave on this element, by the time this source has become 0, this positive charge has made it to the end. And I'll go ahead and then I'll come back. And by the time the source becomes negative, it now has a potential difference with this positive, and this positive is starting to get attracted back. But, sorry, it is attracted back by that time. It is back. So we have maximum positive starting here. 0, she's got there. Negative, it comes back. And that positive charge meets a negative charge. And a positive charge added to a negative charge summarizes to 0 charge. I can't write very well. I can't really see, that's the problem. So, we create a potential difference, it transitions along and comes back and then gets resolved. And of course, exactly the same in the inverse is happening here. So each time, quarter, half, each half cycle, we create a potential, two potentials, or it's still a potential. The transient, and remember, it's a moving charge, and just because it's changed direction doesn't mean it's changed its charge. So we create, let's say, a positive transient. It's creating one rotation that way, and because it's going the other way, it changes rotation, and that's what we call a change in sign on the current flow, but not the charge. Transient one way, transient back. But when it gets back, it meets a negative because a positive here. By the time quarter wave later, 0, half wave later, it's back, but it's met a negative. And we have to add energy each time to make that happen. Now, if the element length was a half wave long, let's say we start maximum positive here. So same thing with the, the degrees. So at the maximum positive, bang. By the time it's gotten halfway along that half wave element, the source has hit 0. By the time it's actually a half wave at the end of the element, the source is now negative. There's now a very significant potential difference between this positive here and the source. So with added enthusiasm, and it has nowhere else to go, it starts to travel back. And of course, like before, it's changed its rotation of the magnetic field, but not its charge. So let's go back. We started positive. By the time it got to 0 at the source, positive reached here. By the time it got to negative at the source, positive reached here. By the time it gets back here, the source is now 0. And by the time it gets back here, the source is now positive. Positive meets positive. Repel, that's negative, negative, same thing. Repulsion, adding, not subtracting, not equaling 0. And of course, that's a high impedance to the flow of current. Because, well, a positive isn't going to want to flow towards a positive. A current is the positive wanting to flow to the negative and vice versa. So, with impedance matching, you can actually create an additive scenario. Now, there's only two antennas that do this, and one of them not so well. The one that's not so well is the end-fed half wave, But it's not so well because, well, I could do better with one. But anyway, but the center-fed full wave, which for some reason seems to be stated that it doesn't work, it can't work, blah, 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 blah. But a center-fed full wave has about 2 dB gain over a half wave. But it's essentially like two end-fed half waves fed out of phase, but they're extremely high impedance, just like an end-fed half wave. The good thing about a center-fed full wave is it has something to feed back on, whereas an end-fed half wave is dumb as dog shit. But yes, do you see my point? Additive with the high impedance, cancelling each half cycle with low impedance. Do you get it now? And when I say, by the way, additive scenario, I'm talking about adding potential. Now, of course, by the time that positive's gotten here, this is sending a negative. And this is the other interesting thing. They're passing each other, okay? But they're constantly chasing each other. So it's a very different scenario.